Now we have to talk a little more specifically about exactly how the action potential actually works. And in order to do that, we have to just revisit this topic very quickly, the idea of ligand-gated channels versus voltage-gated channels. Just so you know, and just so it's very clear, ligand-gated channels only exist in the dendrite and the soma of the neuron. And there's also some in the axon hillock. And the voltage-gated channels only exist along the length of the axon and also in the axon hillock. So that it becomes very important to make this point, because action potentials do not occur through chemically gated channels or ligand-gated channels. Rather, they only occur through voltage-gated channels. And so I'll try to be very clear about the language here, but understand this as a material point, is that when you have action potentials, they only happen through voltage-gated channels, and so they only happen along the length of the axon. So let's take a look at the channels then. As you can see, every single one of them that is shown in this picture is a voltage-gated channel. And there's a few different ones that we're going to be looking at here. For example, voltage-gated channels, there is the closed idea where the gate is closed. The gate is open here, but then there's also a separate gate that is called an inactivation gate, which is present inside of the cell and actually kind of corks the inside of the cell. When even if the channel is actually open, the inactivation gate corks it shut from the inside. Voltage-gated potassium channels only exist in either closed or open states. This inactivation gate is super important. So let's take a look at the same thing that we just looked at here, but let's look at it in terms of channels. The first state is the resting state. Remember that I said at the resting state, in a general sense, nothing is either entering or leaving the cell, and so there's no change in the membrane potential. It's just at rest. The inactivation gate is off, sodium channel is closed, potassium channel is closed. The second stage of an action potential is called the depolarization stage. And in the depolarization stage, what happens is that the voltage-gated sodium channels open. And remember the reason why they open? Remember? If we're talking about the initiation or the generation of an action potential, the reason why they open in the first place is because there was a reversal of membrane potential, where all of a sudden you had a depolarization flowing into the axon hillock from the dendritic region or from the somatic region, from the soma, and that change in membrane potential actually caused this initial state to change. So when the membrane potential changed, it caused this gate to open, this all-important voltage-gated sodium channel to open, and sodium began to flow into the cell. That starts the whole ball rolling. Okay, at stage 2 then, depolarization stage, the voltage-gated sodium channels are open. Voltage-gated potassium channels are not yet open. They're called delayed rectifiers because they do not open right away. They open with a little bit of a delay, about a 1 millisecond delay. Okay, let's see now. The inactivation gate is off at this point. So sodium freely flows into the cell, causing a huge upswing in the membrane potential. All right, and from the depolarization stage, then we move into the repolarization stage. Look what happens. The inactivation gate corks the inside of the cell, the inside of the voltage-gated sodium channel. So, you know, the voltage-gated sodium channel may be closing. Some of the channels may be closing, but in a general sense, there's no way for sodium to actually enter the cell anymore because the inactivation gate has closed. But the voltage-gated potassium channel has now opened with a little bit of a delay, and so potassium begins to flow out of the cell, causing a repolarization. The hyperpolarization continues. The voltage-gated potassium channel continues to stay open for a moment. Potassium continues to flow out of the cell, causing that hyperpolarization, the overshoot through the resting membrane potential. And in this case, the voltage-gated sodium channel is reset. So the inactivation gate is off, but the voltage-gated sodium channel itself is closed. And so that resets it back to where you can get back to that resting state and allow for the whole thing to happen again. And it happens over and over and over again down the length of the axon. Remember, voltage-gated channels are only present in the axon. In a general sense, there's only two of them. There's a voltage-gated sodium channel and there's a voltage-gated potassium channel. As much as it looks like there's an awful lot of detail to this whole thing, there's really only two possible channels present. But they are open, they're basically dotting down the length of the axon, and the whole thing happens again and again and again. So down the entire length of the axon, the upswing of 1, the depolarization state of 1, will cause enough of an influx of sodium that will begin to spread down the length of the axon and will cause voltage-gated sodium channels to open at the next point along the axon. And then the depolarization of those next guys will cause the next ones to open. And so that is how an action potential is propagated. And that is why it is called an all or nothing phenomenon. Because once it starts happening at the axon hillock, it basically can't help but keep on happening down the length of the axon. Okay, so let's just consider the two different types of information transfer that we've discussed here. When we're looking at the level of a dendrite, remember this is called a local potential or a graded potential, and the idea here is that there's some kind of a stimulus and some kind of a locus, and that the voltage change is decremental. Basically, there's an influx of sodium, for example, at the one place, but that can actually that is decremental, or it decays or dies out the further you get away from that original stimulus. However, in an action potential, it's possible to have a stimulus that's, for example, at the axon hillock, that will continue to propagate itself down the length of the axon, where the depolarization stage of 1 will continue to cause voltage-gated channels to open as you make your way down the axon, all the way down the length of the axon. In non-myelinated axons, conduction is propagated through what's called continuous conduction. It's shown right here, continuous conduction. The idea here is that the voltage-gated channels are spaced very close together so that it never completely dies out, it just keeps on being propagated. The handy thing when you have myelin, though, this is called saltatory conduction. So in myelinated axons, which again, the vast majority of axons are myelinated, you'll have a stimulus that you no longer have to have voltage-gated channels spaced so close together. Rather, you have the myelin sheath, and then it basically jumps over the myelin sheath into what we call a node of Ranvier, or a myelin sheath gap, where you'll have several voltage-gated channels present so that you can continue to propagate that action potential. And then you can have another sheath of myelin, and then another myelin sheath gap, or node of Ranvier, where you have more voltage-gated channels present. And this allows for a much more efficient system where you can basically jump from one to the next, and it's a much faster situation. So we could either have a decay of voltage, which would happen in the dendrite or the soma because of a stimulus-gated channel opening, or if you're looking at the axon, you're going to be using voltage-gated channels, and the stimulus is different. The stimulus is different, and the way that it's propagated is different. Sure, it starts to fade out as ions leak in and out, but you always have more voltage-gated channels present in areas that allow for things to happen a lot faster. So the two ways that it happens in axons would be continuous conduction or saltatory conduction.